So let's talk about predicting the future. We're not talking about just getting a single best guess. We're talking about creating a reliable range of what could happen next. Today, we're going to dive into some really fascinating research that completely rethinks how we can be certain about uncertainty. You know when you see a weather forecast, right? It says the high is going to be 75 degrees, but you know that's just an estimate. What you really care about is the range. Could it hit 80? Could it only get to 70? See, we don't just want one number. We want a range that we can be, say, 95% confident in. And that is what this is all about. So in the world of statistics, they have a name for this. It's called a prediction band. The big idea is to create an upper and a lower bound, where you have a rock-solid guarantee, like a 95% probability, that the next real-world data point is gonna fall right inside that range. I mean, that would be an insanely powerful tool, right? Now, the absolute holy grail for anyone doing this kind of work is something called conditional validity. This isn't just a promise that you'll be right 95% of the time on average. No, this is the perfect guarantee. It means that for every single prediction you make, no matter the starting point, that 95% confidence level holds true. It's basically the perfect prediction machine. It sounds incredible, doesn't it? A perfectly reliable predictor you can trust every single time. But, like with most things that sound way too good to be true, there's a catch. And oh boy, it's a big one. And this is where the paper just drops a bombshell. It mathematically proves that this perfect guarantee, this conditional validity, is flat out impossible to achieve when you have a finite amount of data. And let's be real, in the real world, a finite amount of data is all we ever have. So what does this impossibility actually mean? Well, it means that to hold on to that perfect guarantee, your prediction band would have to be infinitely wide. Yeah, sure, predicting the temperature will be somewhere between negative infinity and positive infinity. That's 100% accurate, but it's also 100% useless. So the dream is dead. Okay, so if the perfect guarantee is off the table, what do people do? Well, the most common compromise is something called marginal validity. This approach gives up on being right for each specific case. Instead, it just promises that its average performance across all possible situations will be 95% correct. Okay, think of it like this. The ideal, conditional validity, is like a perfect thermostat in your house. It's always exactly the right temperature. The compromise, marginal validity, is like a broken thermostat. It's often way too hot or way too cold. But hey, if you average the temperature over the whole day, it's technically correct. That's not very helpful, is it? And that's the real danger with an on-average guarantee. It can be systematically wildly wrong. It might be super overconfident in risky situations, giving you a prediction band that's way too narrow. And then, in safe situations, it's too cautious, giving you a band that's way too wide. The average might look good, but the individual predictions can be dangerously misleading. So we're in a tough spot. The perfect guarantee is impossible, and the on-average guarantee is seriously flawed. It kind of leaves you wondering, right? Is there a middle ground? A just right solution that's stronger than the average, but still actually, possible? And the answer is a big yes. It's a super clever concept called local validity. The idea is just genius. Instead of trying to make one guarantee for absolutely everything, you first group similar data points into little neighborhoods. Then you provide a strong, reliable guarantee for each individual neighborhood. And this amazing idea is what led to a brand new method they call COPS, which stands for Conformal Optimized Prediction Set. This is kind of the hero of our story. It's an algorithm built from the ground up to deliver on this much smarter, local kind of guarantee. So how does it pull it off? Well, when you boil it down, it's actually pretty intuitive. First, COPS acts like a slicer, dividing up all the data into these local neighborhoods, or bins. Then, for each one of those bins, it builds a totally custom-fit prediction band. And finally, it just stitches all those local bands together into one incredibly intelligent, adaptive prediction. Okay, that all sounds great in theory, but does it actually work in practice? The researchers put it to the test. First up, they created a synthetic data set where the data starts on one path and then suddenly it splits and goes in two different directions. This is a classic nightmare scenario for most prediction models. And the results are just wow. A typical method, like quantile regression, completely whiffs. It just draws one big, wide, useless band right down the middle, totally missing the split. But COPS? It correctly sees that there are two separate paths and creates two distinct, narrower, and much more intelligent bands. It actually gets the structure of the data. All right, next, let's take it out of the lab and into the real world. The team used a classic dataset to predict a car's gas mileage based on its horsepower. Now, the tricky part here is that the uncertainty isn't the same everywhere. There's a lot more variation in mileage for those big, high-horsepower cars than for the smaller ones. A simple linear model just can't handle this. It creates a one-size-fits-all band, so it's way too cautious and wide for the low-horsepower cars and dangerously overconfident and narrow for the high-horsepower ones. But COPS, it just beautifully adapts. The prediction band starts out narrow and then elegantly fans out, getting wider right where the data gets more uncertain. Now, for the final and honestly the most mind-blowing test. The researchers took COPS and applied it to some seriously complex, messy, real-world biological data, the voltage readings from a neuron in a macaque monkey's brain over time. This isn't some clean, perfect dataset. This is the real, noisy, complicated world. And this is where COPS did something truly profound. It didn't just give a range, it gave a range with gaps in it. At certain moments in time, COPS predicted that the neuron's voltage was highly likely to be in one of two totally separate regions, with a big, empty space in between. And the implication of this is just huge. Any traditional method would have just smeared one continuous band over that whole area, completely hiding what's really going on. COPS, on the other hand, revealed that the neuron isn't just fluctuating randomly, it's very likely jumping between two completely different states. This is more than just a better prediction. It's a potential scientific discovery about how the brain actually works, something that was invisible before.
So let's just recap what makes COPS such a game changer. You get a true, reliable guarantee that works on any amount of data you have. It's distribution-free, which is just a fancy way of saying it doesn't care how messy your data is, it can handle it. It automatically finds these complex structures, splits, gaps, you name it, that other methods miss. And on top of all that, it's as accurate as is theoretically possible. It's the whole package.
What this research really does is give us a tool to be more honest about what we know and what we don't. And it leaves us with this massive question. If we can finally see the true shape of uncertainty, all the splits, all the gaps, all the weirdness, what new discoveries are just sitting there waiting for us? Whether it's in financial markets or medical diagnostics, this is a powerful new lens for looking at the future.